Justin Talamantes.
My name is Felicia Pastrano.
And I'm Christian Garcia.
This is our project on Puckett. So classroom sizes these days are getting bigger and bigger, and because of that, teachers are becoming busier and busier. And it's getting more difficult for them to multitask and monitor their students, especially during testing time. Because of distracting technologies these days, like cell phones and computers, students' attention spans are becoming shorter and shorter, and because of that, their test grades are being affected. So what we want to do is create a product that will improve teacher productivity, it will retain students' attention, and it will help to discourage cheating among students during examinations. And we're hoping to do this all while creating a fun and interactive classroom environment. So our solution is Puckett, which is a puck-shaped device that will sit on a student's desk and monitor sound levels during testing time to discourage cheating. It will also have a game mode, a custom mode that can be used during fun activities. We're primarily aiming for grades of K through 12th grade, but it can be used in any classroom. And we want the device to be unobstructed, and we want it to be versatile enough to handle different situations. So we came up with a few different design concepts. They range from like different constraints like connectivity, how many buttons it would have, how many microphones. And these are some of the constraints that we use in our Q matrix. They include dB noise level transmission to monitor sound levels, the GUI, cost effectiveness, user friendliness, and like I said, we compared different design concepts. We gave each constraint weight, and we came up with these numbers, and ultimately we found a design that was best fitted that Chris will talk about now.
Yeah, so we decided that the best design was actually our first one. But we wanted to create a compact swarm system of pucks that we call the slaves in this case. These are going to be pucks that transmit the signal, and button presses and audio, and they also receive communication so that they get activated or they get switched over to different game modes. We wanted the pucks to be rechargeable. We wanted there to be custom LEDs, buttons, and be able to change the microphone settings depending on the situation. We also wanted to have, our biggest emphasis was the user-friendly GUI. We wanted the teachers to be able to essentially plug and play. We didn't want them to have to read manuals or do any sort of integration with the computer. Everything had it working right out of the box. Another big component was that we wanted to do a 3D printing housing for the slaves and the master, just to have a little bit more cost effectiveness. The requirements, so we do want our software to be able to analyze and detect signals. That was a big one, and then also be able to communicate with the pucks via the master. The master is going to be processing all the signals from the pucks and then transmitting it as well to the computer. So the master is going to be doing a whole lot of work in terms of communication. There's going to be transmitting, receiving on both ends of the slaves and the computers. And then the slaves are only going to be transmitting information. They'll also be receiving, but really they'll only be receiving the change of settings. Some of the design constraints, Python and PyQt5, this is the software that we're planning to use for the GUI and the interface. We're not very familiar with that, so we've been doing research and getting more familiar, working on independent projects and stuff like that. Another constraint was to be able to create a truly custom mode. It's easy to imagine what we want as custom, but it's difficult to allow teachers to have a custom build. Processing issues in terms of A to D. We're not too familiar with sound processing or audio. We're not too familiar with the serial UART Bluetooth communication, so this is all research we've been doing outside. And then of course, things like interference from outside signals and then quality versus price. So our proposed system is going to have a standalone application, again, built on Python with various modes and various windows. Our emphasis is going to be on the application. We do want the microcontroller to be plug and play and be able to receive and transmit automatically through that application using UART ports and communication through Bluetooth. And then we wanted the slaves to be connected using Bluetooth LE modules for their fast response time, their idle power consumption effects, and then to be able to connect things like microphones with buttons and allow that transmission to go over successfully using Bluetooth. This is our hardware flow diagram. It's basically visualizing everything we've been talking about with the power switch, the slaves, the masters, and then the computer. And then the software, this is going to be what's going on behind the scenes in terms of the processing the signals and what happens when things are clicked and how things interact on the back end of the project. This is some of the software that we're using.
This is our material list, so it's going to come out to about $250 for our prototype. That includes 2 pucks and a main unit. Of course, this doesn't take into account broader classroom sizes or also different manufacturers that we may be using. This is our task breakdown. We broke our task down into 4 different phases. Phase 1 being software and hardware. Phase 2 being integration. Phase 3 is fabrication and assembly. And phase 4 is testing. So we're going to start out with software and hardware. And the software encompasses the user interface as well as the sound processing. We're looking to hone in on human voices specifically. So that means we want to filter out background noise such as paper rustling or dogs barking in the background. Hardware is going to be dealing with connections to the main unit, connections between the pucks in the main unit as well as the computer, and taking in that data and how the main unit sees that data. Phase 2 of the integration is merging the hardware and the software portions, so we're making sure that variables line up essentially, and we're not getting any compiling errors when we're running the program. Fabrication and assembly is going to be our shortest phase, and that includes designing the pucks as well as 3D printing them, and then encompassing the electrical circuits in the pucks as well as the main unit. Phase 4 is testing. We're going to be preparing to test our final product as well as hopefully test it in a classroom to make sure that the product's useful at the end of the day in the education field. So our schedule starts tentatively on January 7th. We know that school starts the 14th, so we're looking to get ahead of the game in terms of our research. We're ending tentatively on April 12th. That isn't a hard deadline, of course. We're open to ending before that or a couple days afterwards. But that's kind of just where our deadline sits. So we're starting the hardware and software phase on the 7th of January, like I said on the previous slide. This includes research, but we're starting research as soon as finals end, so we have a bigger gap to just make sure that we're getting all of the research that we need. The software and hardware phases do overlap, so we can start kind of using that research on the programming side and making sure that we're ahead of the game rather than behind. So then we go into phase 2, which is integration. Of course, all of these tasks vary about 3 to 4 days. We're kind of just want to make sure that we have extra days to ensure that if we get behind or we get ahead, we can use them. And that goes through fabrication assembly, which is our shortest, and then testing. And we're ending April 12th, which is around Tech Symposium. Of course, like I said, we're hoping to have a final product beforehand so we can make sure